So I will share the link when we finish this one. I will get you the link, but also maybe this one might be the link. So if you want to get, so okay. So we will go back again to our slides. So can you see my screen?
Yes.
Yeah.
Okay. So today it will be very basic. I know some of you they have a strong background in this area, but we just want to make it step by step so we can build our we can go from a perceptron into deep learning. So as I told you, feed-forward neural network, we can just imagine that we have very simple one. Feed-forward neural network like this one, for example, we have an input layer, and this input layer has two inputs, right? Maybe we have a hidden layer which has three or four, for example, neurons, for example, and maybe an output layer which has just one, right? We have those connections. So in feed-forward in neural network, in fact, they call it connectionist because we have those connections, and its connection, in fact, it has a weight value, and this weight value will reflect how important is this input. So we imagine that we have two inputs, x1 and x2, for example. So this one will be connected to this weight with a weight value called omega 1, for example, omega maybe 1, 2, 1, 3, and so on. And also we have an output layer, and this output layer has the output will be y, for example, and it's connected also using some weights v1, v2, v3, v4, for example. So each unit here, it's a perceptron, right? Or just a unit. We calculate summation here. Summation of inputs multiplied by weights. So it's weighted sum of inputs. So if I need to calculate what is the input here, in fact, I mean this unit, for example, I can just change the color. So this unit, for example, it's connected to the x1 and x2 using omega 1, omega 1, and the omega, for example, 2, 1, for example. So if I want to write the equation of this one, it will be like this one. It will be omega 1 multiplied by x1 plus omega 2 1 multiplied by x2 plus something called bias. We need to, or we can just, if we need to write it in more compact form, we can just say that this one called omega x plus b, or you can just say that it's this summation omega I xi, for example, plus b. You can write it as much as you want, in fact. So we calculate the weighted sum. So the idea here is that the input to this unit will be the weighted sum of inputs. So it will be omega 1 multiplied by x1 plus omega 2 1 multiplied by x2, for example, plus bias. We can do it for each unit. So it will be this vector multiplication, omega multiplied by x plus b. But if you want to make it more compact, we can just use matrix multiplication. So I can go for the 4 units, for example, and I can define the input as a vector. So the input will be this vector x1 and x2. I just call it x, for example. And the weights in this case, it will be this one. Those weights, it will be it should be omega transpose x. So it will be, for example, omega. So it will be omega 1 omega 1 2, omega 1 3, omega 1 4, right? And the second column, it will be omega 2, because 2, it is a second input to unit 1, omega 2 2, omega 2 3, omega 2 4, for example. So now if I want, and also we have the bias. So each unit here is connected with a bias. So we can define a bias vector also. It will be like B1, B2, B3, B4. And using a matrix multiplication, we can make our life very easy. So if I can just multiply omega x plus b, in one step, we will be able to calculate the inputs to each of those units, right? So when we use matrix multiplication, it makes life very, very efficient. So in the first, if I need to calculate the inputs to the first hidden layer, for example, it will be just omega x plus b. If you want to do the same for the output layer or for the second hidden layer, for example, it will be the same. You will get the output from this. I can just call it, for example, it's a z, for example, equals this. And I will multiply for the output layer also. So if I need to find y, so it will be, for example, it will be v multiplied by z, for example, plus the bias here. It could be, for example, b by, for example. So it will be like this one. So the idea here, feed-forward neural network, it's organized in layers, and when we do it in this structure, it will be very efficient in terms of calculation. In feed-forward neural network, we go one time forward to calculate outputs. So first we need to calculate this output. So we need to multiply x by omega and apply an activation function here. And the output will be multiplied by v plus the bias of this output layer here. And we apply the activation function in the output here, and we will calculate output. So we need to go forward to calculate the outputs. And when we calculate the predictions here, we will subtract it from the target value because we need to calculate error. So maybe the error will be target minus y. And we will use this value and we will go backward to adjust weights. First, we will adjust the weights which are connected to the output layer first because this is the closest to us. So we will adjust V. To adjust V, we need to calculate something called the delta V. And we will do those adjustments. And after that, we will go to the next layer. I need to adjust omega here. So I need to calculate delta omega. And we need to repeat this process each iteration, for example, right? Or each epoch. So having this feed-forward neural network organized in layers, it becomes very efficient and very easy for us because we can just use matrix multiplication. If you want to go forward, you just need to multiply x by omega and add to it the bias b, for example, vector. You will apply the activation function also on the outputs, and you will get the outputs from this first hidden layer. You will multiply again the output from the first hidden layer by v, add the bias, and apply the activation function and calculate your y. So it will be very, very simple, very simple, and very quick, very efficient. If you want to go backward, it will be exactly the same, but we need to calculate delta v, and this delta v, it's the rate of a change because we need to change v by a value called delta v, and this v, it will be learning rate multiplied by the gradient, right? It will be eta, the learning rate multiplied by the gradient, error gradient, for example. So we calculate the error here. We need to square this error because when we square it, it will be convex. So we will be sure that we will be able to minimize this error. So first we calculate the error, t minus y, and we will square it. And after that, we will get the first derivative of this error. And we will do this, we call it error back propagation. We will propagate the error backward to adjust to those weights. So we call it learning process. So when we go forward, we call it its inference. For example, we calculate predictions. And after calculating predictions, we will calculate the error and we will go backward to adjust weights. And we will repeat this process all time. So today we want to study the basic unit, which is a perceptron, because this unit, in fact, we call it a perceptron, right? We just need to understand what is going on here in this unit and how can we use it for solving some problems, because it's very simple, in fact, but at the same time, it's efficient. So we can use it for solving complex problems. But the problem here is that it has only one output. As you can see here, this perceptron has only one output connected to it, correct? If you have another unit here, I can get the same output here connected to this one also. So in fact, the output from this perceptron, it's only one. So we can use this one only for binary classification problems, because the binary classification problems, we can assume that the output will be 0 or 1, for example, or +1 and -1. So we can use this perceptron for classifying binary classification problems. So we will study the perceptron first. And after that, we need to know how can we adjust weights of this perceptron, because the perceptron is similar to this one. So the perceptron, we can pick only one unit here. So we will have only one unit. And this unit will be connected to, for example, imagine that we are solving iris problem. So we will have 4 inputs, correct? So we will have x1, x2, x3, x4. Each x of those is connected to this perceptron using weight. So we'll have omega1, omega2, omega3, omega4, and at the same time also we have something called the bias. We will calculate this weighted sum of the inputs. So it will be, we need to calculate omega multiplied by x, and we will add to it the bias. And this equation, we will call it the decision line or decision boundary. So when we are solving a binary classification problem, usually we have the data set like this one. We have one class located in some place. This is one class, for example, and we have here another class, for example. And in fact, we need to classify it. And to classify it, we just need to plot a line which will divide those two classes into two separate classes, for example. So we need to find this line. So in fact, the equation omega x plus b equals 0, for example, this one, it will be the decision line. We need to find this decision line. And as you can see here, this decision line, it's just line in two-dimensional space. And we have two classes. All data points which are located above this line, it will be classified as circle, for example. All data points which are located below this line, it will be classified as plus. So that is the whole story. If you want to classify a problem, for example, we just need to find this decision line. And after that, any point which will be located above this line, it will be classified as circle. All data points which are below this line, it will be classified as plus. So this is the whole task. This line has some parameters. The parameters of this line, it's omega and b. If it is in two-dimensional space, we can say that we have two features, x1 and x2, for example. In iris dataset, for example, it could be beta length and beta width, correct? So we have x1 and x2. So the equation will be omega 1, x1 plus omega 2, x2 plus p equals 0. So this is the decision line or decision boundary. And our task, in fact, is to just find what is omega 1, what is the best value for omega 2, what is the best value for b, right? Omega 1 and omega 2, in fact, it's the slope of this line. So when you change omega 1 and omega 2, you will change the slope of this decision line. So for some values, the line will look like this one. If you change it, the slope, maybe you will get another line like this one. And of course, you will have endless number of lines. So what is the best combination of omega 1 and omega 2? This is the question, in fact. So we need to answer this question. What is the best value for omega 1 and omega 2? So we can get a line which will give us an accuracy of maybe 95% or 99%. Because I can select a line here, for example. Maybe this line will give us accuracy of maybe 85%. Someone else, he will select a line which looks like this one. Maybe in this line, he will get an accuracy 10%. So the idea is to find a good combination of omega 1 and omega 2 so that we can get better accuracy. Of course, you can find omega 1 and omega 2 manually. If your data set is in two-dimensional space, you can plot the data points and you can find omega 1 and omega 2 manually, in fact, or by trial and error. And test your system. If the system gives you good results, it's fine. Otherwise, try to find another combination. B here, it's the bias. And this bias, in fact, it's the intersection with y-axis. This intersection here. You see this intersection? This is B, in fact. So it could be positive number, it could be negative number. If it's negative numbers, the line will go down. So in fact, the bias, it will shift the line up and down, correct? So you can go up and down. So it will give you more degrees of freedom, more freedom to select a good line. But if you selected B equals 0, for example, this line must go through the origin, this point here. So in this case, I mean, you have, limitation. So you can train, for example, a perceptron without bias. You can just say that, okay, I will not use a bias, I will put B equals 0. If you will select B equals 0, you need to know that your line will go through the origin, right? And in this case, when you change omega 1 and omega 2, of course, you will rotate the line across the origin, but it will make some limitation for you because maybe your data set is located in some location and you need more degree of freedom. You need to move your line up and down. So if you want to move your line, decision line up and down, you need to allow B to be changed to be positive value, negative value, for example. So at the end, this is the basic unit of the feed-forward neural network. And of course, using a single perceptron, you have some limitations because you can solve some problems, binary classification problems. But if your data set is very complex, maybe one perceptron will not be enough. And we need to combine many perceptrons into a layer, for example. So we can create an input layer. We can create number of hidden layers. So just connecting those perceptrons together and try to make a system or a model which is more complex because it will contain more parameters. So in this case, your ability will be much better because just for this simple case, if you have this perceptron and you have two features, x1 and x2, you will have 3 parameters here, right? We will have 3 parameters, omega 1, omega 2, b. If you will increase this number, for example, to 1,000 parameter, of course, your abilities will be much better. But of course, also, the cost will be high. You need more data to train your model. you need more computational resources because your model now is more complex. So today we will talk about the perceptron and how can we adjust those weights. Maybe we can do it manually, for example, but if you need to adjust it automatically, we need to learn something called the perceptron learning rule. This perceptron learning rule, it's the error bag propagation algorithm, which is used in a perceptron. It's not error bag propagation, but it's a very simple rule which is used for adjusting those weights. Because for simple problems, we can find omega 1 and omega 2 manually, but in this case, it will not be data-driven method, right? Because data-driven method means we learn from data. If you will adjust it manually, in this case, we will not be able to learn from data, and it will be just very simple, right? It will be like a regression model, for example. So perceptron learning rule, it's a very simple rule which will help us to adjust those weights automatically from data. So we will use our data set for training our perceptron, and we will run this one for a number of epochs, for example, until we are happy with the performance. Maybe until the performance was 95%, we can just say this is fine. And it's linear line, but in fact we can make many things more complex. Maybe next week we will talk about it, because I can make very complex shapes by playing with those with the decision boundary here. Also, we will talk about this adaptive linear unit. This adaptive linear unit, it's exactly the same as a perceptron, but with linear activation function, feature scaling, and we will use some examples. So we can just go directly into that part. So yes, maybe you need to clean. Okay. I want to clean this. Okay, annotate. Yes, clear. Yes. So the perceptron, it's a basic unit. The perceptron is a basic unit of artificial neural network. We call it neuron, for example, artificial neuron, and it can classify a task into two classes, 1 and 0, for example, or 1 and -1. So it's according to the activation function. So you can use an activation function where the output will be 1 and 0, for example, but also we have another activation function which will give you this function, for example. It can give you two outputs, 1 and -1, this one. So we can get here 1 and -1, for example. There is another activation function, for example, if net equal 1 and 0, for example. 1 if net greater than or equal 0. So all points which are located above the line will be classified into 1, and all other points or the points below the line, it will be classified into 0. This function here also, it's the same. So if net equal 1 and -1, which means all points which are located above the decision line would be classified into 1, and the other points which will be classified into -1. So this basic unit classify problems or tasks into two classes, 1 and 0, for example, or 1 and -1. The decision function can be defined as a linear combination of input values xi, those are the inputs, and the corresponding weight values omega I, right? So this is a decision line, as you can see here. So net equal omega 1 x1 plus omega 2 x2 plus omega n multiplied by xn plus bias. So if we need to draw this one, it will be like this one. I have a unit, and this unit here, I can just make it for two inputs, because when it's two inputs, we can just plot it in two-dimensional space. But when it's three inputs, of course, for three inputs, we can multiply the decision line in three-dimensional space. But when it's 4, it will be difficult. So imagine that we have x1 and x2, for example. x1 will be connected using omega 1. x2 will be connected using omega 2. We have bias value here. We will call it B, for example. And we have here the weighted sum. And after that, we will calculate this value. We will call it net, right? So net equal omega x plus P. So net equal, I can write it in more compact form. It will be omega x plus P. But you need to define x as a vector, and you need to define y as a vector, omega as a vector. So x will be x1 to xn, for example, and omega, it will be omega 1 to omega n as a vector. So we can just write it as a vector multiplication omega transpose x, in fact, omega transpose x. Because the output from this one must be scalar. So it will be omega transpose x plus b. B, it's the bias. We know that omega 1 and omega 2, it will control the slope of the line. B, it will shift your line up and down across y-axis. So it will go up and down. When it's positive, it will be above 0. When it's negative, it will be below 0. For example, when b equals 0, this line will go through the origin. So it will be omega transpose x plus b. And after that, I need to apply an activation function because I will calculate net. We need to apply here an activation function. So this activation function, in this case, it will be like this one. So this will be the activation function, right? So now it's just converting net into +1 and -1. So in x-axis, we will have net here, and in y-axis, we will have y, correct? So the output will be y. So in this case, y or f equal 1 or -1. It will be +1 when net is greater than 0. Do you see that part? So when net is greater than or equal 0, maybe it's not that part, right? When net is greater than or equal +1, +0, for example, the output will be +1. Otherwise, it will be -1. So I can use this kind of activation function. You can just invent your own activation function. There is another activation function. We call it hard limb, for example. This hard limb will look like this one. So it will be like this one. So it will be like this. So what will be the output in this case? So if we will use this one, what will be the output? Yes. So this is net. This is f net or y net, for example. So in this case, this function will be +1 and 0. It will be +1 when net is greater than or equal 0, 0 otherwise. Right? So just any activation function, I mean this activation function, it will translate this weighted sum value into something which makes sense for us. Because I need imagine that we need to classify iris data set. So we need to classify it into +1 and 0, for example. So in this case, I need to select an activation function which makes sense for us. We will select this one. If your target value in your data set is +1 and -1, you need to select this one, for example. So it's according to your data set and according to your problem, you will select an activation function which will help you to solve your problem. It should make sense for us. So for example, if my target classes are +1 and -1, and I cannot select 0 and +1 because the error will be very, very large, and I will calculate wrong error value, and I will not be able to adjust my weights. Yes. Weights, I mean, here it's weights cause rotation of the decision line, and the bias, it causes translation of the decision line. It will translate the decision line up and down, and the weights will cause rotation. Weights will adjust, I mean, just imagine those weights are the slope of the line. When you adjust omega 1 and omega 2, you will change the slope of the line, so the line will rotate. The decision boundary with the decision line will rotate in your how do you call it? I mean, x and y coordinates. It will make your line rotate, but the bias will translate your decision line. It will go up and down. Yes. So this model, in fact, it's inspired with this biological neuron, and this biological neuron, we have a cell body here, and this cell body has some inputs, which is, for example, x1, x2, xn, and those inputs are connected to this cell body using dendrites. And those dendrites, in fact, it has some chemicals, and it has something similar to the weights, because it transmits. It's like a wire, for example. So it's connecting the signal to the cell body, and some of those connections have high resistance, and some of them has less resistance, for example. So how can we model it in mathematics? We can model them in mathematics by weight. So this weight value, it can be very large value and it could be also very small value. I mean, we have these weights. So imagine those weights equal 0. It means it's a wire which has a resistance equal infinity. When omega equals 0, we will multiply, for example, x1 by 0. So the model will not be able to use x1, right? So in this case, it's like a wire, and this wire has a resistance equal infinity, for example. When omega, for example, equal 1, it means we will be able to measure this x1 and we will feel it. When omega equal 10, for example, it means we will try to magnify this signal, which means this signal is very important for my problem. So you are solving a problem and you have two features, for example, x1 and x2, for example, and you discovered that omega 1 is larger than omega 2. It means for us, in fact, is that maybe x1 has more importance than x2. We can just reflect, we can explain it like this. Maybe x1, feature 1, for example, is more important for my problem compared to x2, for example, and therefore omega 1 is higher than omega 2. So this value, in fact, when it's small, when it's a negative, when it's a very large positive value, very small negative value, it will reflect the importance of this feature, for example, for my problem. And we will not adjust it manually, but we will try to let the model try to find this value by itself using an optimizer. So here in this cell body, it will calculate this weighted sum, omega multiplied by x, and after that, it will maybe apply some activation function, and it will make decision, and it will send it to other layers or other neurons, for example, using those axon terminals. So anyway, it's inspired by the biological neuron, and they modeled it using a perceptron, and they used it in 1940 in many applications. But at some point, they discovered that it's difficult to use this one for solving very complex problems. And they have something called the dilemma of artificial intelligence, because they give promises, lots of promises to people at the time that they discovered something which can solve, I mean, all our problems. But they discovered quickly that this perceptron has very limited capacity. So in this plane, for example, we have here, you can just imagine that x-axis is represented by x1, for example, and y-axis it's represented by x2. We need to solve this problem. We have two classes, the red circles and the yellow circles. So we need to find this decision line. How can we find this decision line? This decision line will be represented by this equation omega x plus or minus b equals 0, for example. This is my decision line. And the idea here is to try to find a good combination of omega 1, omega 2, and b, so we can find a line which can successfully classify those two sets into two different classes, for example. So in this case, all points which are located above the line will be classified into +1, and all points which are located below the line will be classified into -1. So the neuron, in this graph here, we have number of inputs. We have x1, x2, and xn, for example, and each value is connected with the perceptron using a weight value omega 1, omega n minus 1, omega n, for example. This one, it's a bias, so just forget about this one, but it's a bias, because the bias, it's just a weight which has an input equal 1. So you can classify it, you can just write it like this one. So you can put it here, for example, we have here a bias plus p, correct? Or you can just explain it as a connection, and this connection has an input equal +1, and the weights here, the weight value here called b, for example, so it will be the same. Or if you want to make your model as compact, because my model, in fact, we are writing it like this one, omega x plus b equals 0. This is my decision line. But in this graph here, when you define the bias as a connection with an input equal 1, I can just simplify this equation into omega x equals 0, because in this case I will consider that this bias it's just a normal input which has an input equal +1, for example. So in this case my weights will be like this one. It will be, for example, omega 1 or omega 0, omega 1 until omega n multiplied by x, and in this case x will be 1, x1 until xn. So you can just make it like this one. And of course, it will be omega transpose x. So if you want to simplify your model, you can just define this weight as a normal input with normal connection with a constant input equal +1. And this is a activation function, and we call it step function because, as we mentioned before, the perceptron can be used for classifying binary classification problem. So we need to use this step function. This step function will be my activation function. So we need to calculate net, and after that we will apply this net to this activation function to calculate the prediction. And when you have the predictions, you can calculate the error and you can adjust your weights. Yes. How can we use this perceptron learning rule? The perceptron learning rule is very simple. But maybe should we take an example first before using perceptron learning rule? So, for example, imagine that we have this AND data set, for example, or XOR data set, for example, AND or for example, not XOR because XOR is complex. Maybe you can use AND data set, for example. We have two inputs, and we need to classify it into two classes, and we need to find a good decision line which can classify AND data set into so I will just if you can see my screen, I will just try to create a new slide here. In AND data set, can you see my screen?
No.
Nope.
Okay. Yes, I will share one more time. Sorry, share my screen. So please, we will have sample problem. Do you know the truth table of XOR, for example? So we have this table. We have two inputs, X1 and X2. This one, it's a 0. It's a 0, 1, 0, 1, 0, 0, 1, 1. When it's AND, for example, what will be the output? It will be 0, 0, 0, 1, correct? So we need to, when we plot it in X1 and X2, so we will have here, we have here X1, we have here X2. So we need to plot our data set. So when it's 0 and 0, it's 0. I will make it circle. When it's 1 and 0, it will be here. It will be circle. When it's 0 and 1, so it will be here. X1 is 0 and X2 is 1. It will be like this one. And when it's 1 and 1, it will be square, right? So now we have two classes, correct? We need to develop a perceptron which will classify, because this is a data set, and we need to find a line which will classify this data set into two classes. We have circles, we have squares. So of course the line will look like this one. I mean, we need to find a line which look like this one, because this is a very good line, correct? Right? So we need to have this line, because this line will classify the data set into two different classes. All data points which are located above the line will be classified as squares, and all data points which are below the line, it will be classified as circles. So this is a perceptron. So I will draw the perceptron for you, and I will let you find the weights. So we will have this perceptron, and this perceptron will have two inputs. The first one is X1, and the second input is X2. X1 is connected by omega1, X2 is connected by omega2. We have here a bias value, right, which is B, correct? It's a +1 or just B. We need to find this weighted sum, and after that, we need to classify, we need to use any activation function. We can just use step function. we can use any step function. So it will be like this one. So for example, we can make it like this one. Yes. So now the task, please, is to find this line. It's omega x plus b. I mean, this line, it's parametric. So in fact, if we need to describe this line, it will be omega x plus b equals 0. I will say it's omega transpose x plus b equals 0. If you want to write it in more details, so it will be omega 1 x1 plus omega 2 x2 plus b equals 0. So please find omega 1. What is the value for x omega 1? What is the best value for omega 2? What is b? Because this is it's like optimization problem, or this is a perceptron, but so try to find it, please. I mean, if you want to find omega 1, omega 2b, it's equation of line. So we need to find the intersection here, because this point is 1. Remember, this point is 1, this point is 0, this point is 1, this point is 1 and 1. So we need to find a line which will intersect here at some point, maybe at 1.5. And also we need to find a line here which will intersect here, maybe at 1.5, for example. Correct? So now you know 2 points. You know 2 points, 1.5 and 0. And this line also, it's 0 and 1.5. Or you can say it's 0 and 3 divided by 2. So you have one straight line and you have 2 points. From these 2 points, please try to find omega 1, omega 2, and b. Right? And also, it will be nice if we can implement it and if we can see if it will classify my problem. If you want to implement it in Python, so this is my data set, right? So this one will be one vector. This one will be, I mean, this is my data set. It consists of 4 examples, right? My data set consists of 2. So anyway, x will be just one vector, x1 and x2. And you need to find omega. Will be omega 1 and omega 2. You need to find those values, right? You will find it. And of course, b. And if you want to test your system, you just need to find net equal omega multiplied by x, omega transpose x plus b. And we need to apply this activation function, the step function. This step function, it's very simple. If net is greater than or equal 0, for example, the output will be 1. Otherwise, the output will be, for example, 0. Correct? Because we will assume that all points which are located here, it will be classified as 1. This one will be classified as 1. This point will be classified as 0. This point will be classified as 0. This point will be classified as 0. I mean, this is correct. I mean, this is according to our truth table here. So this is the target. You can just say this is a target value. Call it target value. Yeah, so maybe we can use 10 minutes or 10-15 minutes and try to open a file in Google Colab and try to implement this problem. So first you need to find the value of omega 1, omega 2, and the bias. And after that, you need to implement it in Python. So in Python, it will be very simple. It's just matrix multiplication. You need to define omega. You need to define x, correct? Of course, you need to put it in a for loop because I have 4 examples. So this is my data set. You need to define your data set. So I have 2 features and 1 target value. And after that, you will run this algorithm in a for loop. So for this one, for example, x equals those values. For this x equal 1, 0. For this x equal 0, 1 and 1, 1. Apply those values and see if you will be able to classify your data points correctly. Is it okay?
Do you mean to implement the algorithm, or do you?
Yes, please. Not the algorithm, just this example. You need to implement this example in Python.
So do you mean to, for instance, use a library to use a classifier that is existing?
No. We don't need any classifiers. No, you don't need. You just use a perceptron. We will not use any libraries. We don't need to use anything. This is my data set. You need to find the slope of the line and the bias manually.
Okay. Okay.
And once you define it manually, you put it in this vector omega and b, and use matrix multiplication to calculate this value omega transpose x plus b, and apply this step function. We have this step function. You need to define a function, or just if net, just 2 lines. Maybe you can share one screen.
And then we, let's say, train the perceptron by ourselves.
No, you don't need to train. The model is trained. You will find those numbers manually, correct?
Okay.
Sorry.
Yeah, I mean, yeah, I think
you need to find omega 1 and omega 2 manually, and the bias manually.
Exactly.
And because we will not use any optimizer, next step we will use the optimizer. We will use PLR, perceptron learning rule, which will help us to find those numbers automatically.
I agree. That was what I meant by training to set omega.
Yes.
Okay.
Just one question, sorry. Can we just, because it looks like just a simple kind of linear equation, can we just solve it and get the results? I mean, I think we might need to even like write Python code, because if you use kind of like MATLAB, I don't know, Octave, you can do this, I suppose.
Yeah, this is fine. Just do it on paper now, right? Find the equation first, because this is the straight line. Find the equation of this straight line. Try to find the omega 1 and omega 2 and the bias, and test it on paper.
Okay.
And after that, if you can put it in Python, it will be fantastic, because it will help us also to develop our skills. And please, in here, we can, if you want to meet other groups, for example, we can make this, how do you call it? So if someone want to, we have this breakout rooms, for example, if people want to work together. So we can make 2 groups. Is it fine? Or 3-4 groups, people can work together in groups?
Sure.
So people can work together. So participant can select maybe. I don't want to clean my screen. For example, you can make 4 groups, for example, and people can select automatically. So I didn't use this before. So should I make it by myself, or? I don't know. Maybe I can. So just please work together and try to open this file in Google Colab, for example, and try to solve this problem. But in this case, I will, maybe you will not be able to see my screen. So as you can see here, I have some solution also. I can share this one with you. So you need to find omega 1 and omega 2, and you need to find the bias B for example, for O and AND. And after that, you need to implement hard limb function. It's very simple. It's a step function, which has two outputs, +1 and 0. So it's very simple. You don't need to use it from any package. And just test your, we will not train our model. We will just